Hello, we are Group 7 and this is our final presentation of the group project. Our team consists of Liam Graham, Samuel Mallet, and myself, Kyewon Song. Without further ado, I'll begin with a summary of the three technical papers we found. Our first paper is called The Genetic Algorithms for Evolving Computer Chess Programs. This paper was written in 2014 by Omid David and others. This research presents an approach to develop a computer chess program using genetic algorithms, GA for short, focusing on two primary aspects. First, evolution of evaluation functions, and second, evolution of search mechanisms. The authors used GA to evolve both the evaluation function and selective search mechanisms of a chess engine. The parameters of the evaluation functions were initialized randomly and then evolved by learning from a larger database of grandmaster level chess games. This aimed to create an algorithm that mimicked the way grandmasters play. After the evolution, a second phase called co-evolution was applied. This is where best evolved chess engines played against each other. This allowed the search mechanisms and evaluation functions to improve further by learning through competition. The authors then tested the evolved engine against established programs, where it was found that the evolved chess programs performed impressively. This engine even outperformed two-time world computer chess champion Crafty, proving to be adaptable and capable of playing strong chess. This highlights that GA are feasible methods to evolve chess engines without prior tuning. The second paper, Chess AI Competing Paradigms for Machine Intelligence, had been written by Shiva Maharaj and others in 2021. This paper compares two chess engines, Stockfish and Leela Chess 0, LC0 for short. They are compared by using a challenging chess problem called Plasket's Puzzle to examine their performance abilities. Stockfish is an algorithm based on alpha-beta pruning combined with evaluation functions that have been enhanced using a neural network called NNUE. LC0 utilizes deep reinforcement learning, relying heavily on deep neural networks to evaluate positions and determine optimal courses of action. The Plasket's puzzle is known to require multiple deep calculations and precise tactics. Interestingly, the authors also assessed the creativity of the two engines in finding unexpected moves similar to how a human player might use. The study found that Stockfish significantly outperformed LC0 in solving Plasket's puzzle, while Stockfish efficiently found the solutions with combinations of deep search and broad evaluations. LC0, even after extensive computation, failed to find a correct solution for the puzzle. The findings suggest that broad and heuristic-based search approaches of Stockfish is still more effective for specific complex puzzles compared to the deep learning approach used by LC0. The last paper is called Implementing the Chess Engine Using NNUE with Negamax Algorithms, written by Angad, Mackland, Chitale, and others in 2024. This research implements advanced neural network technologies with traditional search algorithms to improve chess engine performances. The paper combined the efficiently updatable neural network NNUE with the Negamax algorithm. NNUE refines piece values during gameplay, providing more context-sensitive evaluations. Negamax algorithm is an optimized variant of Minimax designed to evaluate both positive and negative outcomes, making it faster to identify optimal moves. Alpha-beta pruning was also applied to reduce unnecessary branches during search, improving the engine's efficiency. This search engine was named StockDory and was tested against Stockfish, a chess engine that was mentioned in the previous slide. The paper focused on analyzing complex chess games involving different playing styles. The results show that Stockfish still outperformed StockDory in most scenarios. Stockfish excelled at analyzing both playing style and positional tactics. However, the paper found the StockDory to demonstrate improved computational efficiency and speed. The paper highlights the potential for neural network-based evaluation combined with efficient search methods to advance AI in chess.
For our presentation, we will be utilizing two engines from our found technical papers and compare the chess engines across several games. For the simplicity of our engines, we have decided to use two models that are freely available by developers: the Stockfish 17 and LC0 version 0.031.2. Stockfish is a powerful open source chess engine developed by a community of contributors. It uses traditional alpha beta pruning and deep search techniques to evaluate positions. It relies on rules like material balance, piece activity, and king safety. On the other hand, LC0 is a neural network based chess engine inspired by AlphaZero. It evaluates positions using patterns learned from numerous self play games and relies on Monte Carlo search for move selection. The website we retrieved the engines from are cited in our reference. For the sake of our experiment, we will be conducting the games inside the chess software Arena Arena version 3.5.1. Arena is a free chess engine designed for analyzing games, playing against engines, and managing chess engines. It can support multiple chess engines playing at one time and allows users to run games between engines or play against them directly. Our experiment will be divided into two parts. In test 1, we analyze the performance of both engines by running them through 3 different endgame puzzles. 2 are fairly simple, and the last one is rather complex. And then our second test will involve both the engines competing directly against each other and making observations about their performances. Alright, so as I stated before, our project is split into 2 different experiments. Experiment 1 is the required testing of the 3 different game states, where we compare the performance of Stockfish 17 and LC0 using the popular endgame chess puzzles. We will compare the sequence of moves that both engines suggest, as well as the number of moves it took the model to complete the puzzle, if they completed it all, that is. In addition to the required test, we will also judge the 2 models based on how well they play against each other. In a normal game of chess, both engines will have 5 turns playing in the white position, meaning we will have a total of 10 game rounds. The number of wins, losses, and ties for each engine will be recorded, as well as any notable behavior during gameplay, and the average time left on the clock at the end, which helps indicate the general computational time of the models. Alright, so in this first simple endgame puzzle called Mate with 2 Rooks, White has 2 rooks still available and aims to checkmate Black, who is left with only 1 king. The white boxes on the side show the evaluations calculated by 2 chess engines, Stockfish 17 and LC0. Stockfish 17 calculates the exact number of moves needed to force a checkmate, while LC0's analysis, typically based on probability distributions, is converted here into traditional cent-upon values. For example, Black's score of minus 107.27 reflects a position that is overwhelmingly losing. Both engines predict that the game will conclude in 9 moves, ending with Black's resignation. However, their approach to this outcome differs significantly. Stockfish uses a direct and efficient sequence of moves to secure the checkmate as quickly as possible. LC0, on the other hand, takes a more dynamic approach. This difference becomes especially apparent in White's 7th move. LC0 chooses a surprising and non-intuitive rook maneuver, which doesn't immediately pressure Black, but appears to set up a longer-term positional advantage. If Black had not resigned after the 9th move, this strategic decision might have paid off further on. In summary, while both engines achieve the same result, LC0's move selection showcases its neural network's ability to balance dynamic play with long-term planning, which contrasts with Stockfish's focus on efficiency and precision. Alright, so this next instance, Mate with Queen and Rook, plays out very similarly, and it mostly reaffirms the results that we see in our first game instance test. But in this instance, we have a fairly simple puzzle in which White still has their queen and their rook, and Black still only has their king. White is holding out in the bottom right corner with their queen on g1, their king on h1, and their rook on f1. Meanwhile, Black is in no man's land on d5, and White must mate Black. And in each of these test cases, both respective models control both the black and white pieces. What is interesting is that while both models were able to mate in 5 moves, the way each model goes about putting the other player in mate is very different. Of course, the outcome is the same. White wins and mates in 5 moves, but it does highlight how effectively Stockfish performs compared to LC0. When we look at turn 4 on both games, we see that up to here, the games have played out somewhat similarly, with maybe some slight differences, but they're in very similar positions, with the queen chasing the king and the rook staying back to apply some strategic pressure and map control. However, when the models go to move their rooks for the first time, Stockfish opts to put the king in check immediately, likely because, as we referenced before, putting the king in check is particularly rewarding for the model to make that move. But LC0 moves to C1, which is actually one space to the left of the king, cutting him off from moving farther right. It's an invalid move, and forcing black into the bottom right corner, which is where their king is, restricting their movement. It's difficult to say that this is an objectively better move, as both models achieve very similar outcomes, but the moves that Stockfish 17 selects feel much more algorithmically selected, while the neural network structure of LC0 definitely seems to make it feel like a more creative player, even if a slightly less effective one.
For our third test, we tried Plaskett's Puzzle. Plaskett's Puzzle is a famous chess endgame puzzle named after James Plaskett, a British chess grandmaster. The solution begins with the move Knight f6, which sets up a winning position. But this sequence is far from obvious and requires the solver to think several moves ahead. For our experiment, we ran both Stockfish and LC0 on this puzzle to evaluate their ability to handle this level of complexity. Each algorithm was given 1 hour to find the solution, but neither engine was able to solve the puzzle within the time limit. This was likely due to the constraints of my machine, which used Intel i7 1370p CPU, integrated graphics, and 16 gigs of RAM. While this setup is capable for many tasks, Plaskett's Puzzle requires immense computational power and extended time for an engine like Stockfish and LC0 to explore the depth of moves needed for the solution. It's important to note that other people have successfully solved this puzzle using Stockfish, but typically with more powerful hardware and optimized configurations. Stockfish has the capability to find the correct move sequence, including Knight f6, but the processing demands are significantly higher than what my machine could handle within the 1 hour window. This highlights the importance of both algorithmic strength and computational resources when solving extremely complex puzzles like this. Overall, while this test demonstrated the inherent limitations of LC0 and Stockfish, it also reinforced the potential of Stockfish when given the right conditions. Plaskett's Puzzle remains a significant challenge, but it's a reminder that even the most advanced chess engines require the proper tools and time to perform at their best. For a sort of fourth test, we put the two engines against each other to see how they would perform in a real game setting. We had them play 10 games against each other, and they were all ties except for Stockfish winning just one. As you can see, both engines were fairly equally matched in terms of game outcomes, with the vast majority of games resulting in draws. These draws were often the product of both models making the same move over and over again late into the game, which forced a draw. There was only a single win, with LC0 resigning. There was not a single instance of mate throughout all 10 games. There were also multiple instances of the models taking every piece on the board, leaving only their kings. This resulted in a game ending in a draw, as neither model would have been able to win. It should also be noted that LC0 was much more prone to using all of its time. While both models often had very little time left on the clock, LC0 was often within 1 second of being forced to resign. Of course, results may be different on different hardware, but the consistency with which LC0 came close to running out of time shows that Stockfish is likely more computationally efficient. Something else to note is that when the games first started, the models would take several seconds to determine their optimal move. However, as the game went on and fewer pieces were on the board, the models could make a move before the clock even had a chance to change. This is due to their search space being reduced dramatically. However, it is interesting to make note of and could inform future experiments. In conclusion, while LC0 and Stockfish often select different moves, their overall performance in terms of achieving results is very similar. Both engines are capable of reaching similar outcomes, typically within the same number of moves. However, there are some clear differences in how they approach decision making. Stockfish tends to prioritize moves that produce the most optimal outcome in the current moment, maximizing immediate gains. In contrast, LC0 often makes moves that, while not always the most efficient, set up positions that are strategically deeper or subjectively more interesting. This difference reflects LC0's focus on long-term planning and creativity, a result of its neural network-based learning. When we set the two engines against each other, their strengths and weaknesses become more evident. While they are very evenly matched in many respects, Stockfish demonstrated a small but significant advantage. This advantage allowed it to force a resignation in one of the games, showcasing its ability to identify and capitalize on winning opportunities more efficiently. Another notable observation was Stockfish's ability to infer the best moves faster than LC0, particularly in scenarios where the board begins to clear and fewer pieces remain. In summary, both engines are exceptional in their own right, but their strengths cater to slightly different aspects of gameplay. Stockfish excels in precision, speed, and immediate optimization, while LC0 brings creativity and long-term planning to the table. Both models continue to push the boundaries of what artificial intelligence can achieve in chess, and their differences make them valuable tools for players and researchers alike. Here is a list of the references we used for our presentation.